Hello and welcome to this tutorial on the user analysis code. I'm Katie, I'm one of the authors of this code. I worked on this along with Pierre Hermenia on our final year project working with terahertz spectroscopy. I can assume if you're watching this that you are also working in terahertz spectroscopy. I'm going to assume a very basic knowledge of terahertz, the TeraView system, and the processing of the data that you're going to be gathering from those measurements. This code is purely to look at the analysis of that data. So that's kind of the level I'm assuming you're at. From there, let's get started. So I'm going to run through this for an example using data that I gathered with Pierre from a protocol that we carried out looking at skin tone variation. So to give you a rundown of the kind of measurements we're looking at, we measured the volar forearms, 3 different regions on both the left and right arm. Left as control, right as product applications. 3 different products were applied. We measured controls prior to any application, 10 minutes post application, and 30 minutes post application. So we're looking at 6 different measurements, 3 different rounds. That's the kind of layout we're looking at. So with that in mind, let's have a look at the code for that example. So as you can see, there's a little bit of a preamble here that takes you through what the code is doing, explains that, you have your input parameters, that you're going to load data, and explains a little bit about what should be in the folder with this user analysis code. So I'm assuming that you came along this in that folder. There'll also be a README file in like just a little doc text, and that talks you through the code. Hopefully between this example and that explanation, along with the preamble and any comments within the functions, you are able to understand how to use this code and adapt it. If at all you have any questions, Pierre and I's email addresses are right there. Feel free to contact us at any point. If you have a question about how the code works or what you can use it for, anything like that, feel free to contact us. As you can see, there's a little bit of a version history there that explains, when separate parts were added and sort of different sections that were included. If you find any bugs in this code, also feel free to let us know, because obviously we'd be happy to update those. And you are welcome to adapt this code to any kind of measurement protocol that you want to look at. So with that in mind, let's get started on the first section. So when you're carrying out your terahertz measurements, you're going to be using settings on the TeraView system. So be that your number of repeats, your waveform rate, your sample averages. Here's where you input that data form. So your number of samples is going to be your number of repeats plus 1, how many waveforms you take. Your waveform rate is going to be how frequently you extract those waveforms, and then your sample averages is whatever you set it to there. So with us, we did 199 repeats for 200 samples, so a wave rate of 30, and a sample averages of 5. So then I can run that section. Those values are going to appear in my workspace ready to use. Moving on to the next section, once we've looked at our measurement settings, we can look at the values for the analysis itself. So here's what we want to think about. What kind of values am I wanting to extract here? How frequently do I want to look at that data? Within what range? So you have here some start and end frequency values. So your terahertz data is going to go from a range of 0 to 60 terahertz. You can't look at skin for really more than 1 terahertz, right? So you're going to want to limit your sample frequency range to just be between, say, 0.1 to 1.1 terahertz. And that would correspond to values of about a start frequency of 10 and an end frequency of 70. Then you might want to move on to, do you want to extract data throughout the occlusion process? So say you want to extract from 5 seconds after the start of occlusion, every 5 seconds from there. So say you want to go at 5 seconds in, 10 seconds in, 15 seconds in. Then you want to set your occlusion delay and your increment to correspond to those values. So as you can see here, I've written that your increment and your occlusion delay values are basically the number of seconds times by 6. So say you want 5 seconds into occlusion, you want an occlusion delay of 30. You want to extract increment of every 5 seconds, you want an increment of 30. And then also say you want to extract your values for refractive index and absorption coefficient, then you might want to set an extraction frequency. So again, I've given you a little equation of the value you want to set. So for this example here, I want to extract at 0.5 terahertz. So that's a pretty common value you're going to see in papers for sampling of those kind of values. So for about 0.5 terahertz, you want around an extraction frequency of 34. I've input all those values that I want. I can run section. They're going to appear in my workspace ready to use. Now I've got my values for sampling. We go on to the data itself. So I'm going to have expected you to put in your own little bit of work here. You need to have processed your data files. So you extracted, when you took your measurements, they were TPRJ and H5 files. And then you're going to load those into probably the processing code that Hannah gave you. And you're going to run that through to process your data and save those as .mat files. Now what I want to do here is load those .mat files in order to carry out analysis on them. So I'm going to go through here onto my data. I'm going to select participant, the participant Adam. He was a Fitzpatrick scale 1. If you're looking at skin tone, he was really, really pale. I'm going to load those values here. I've already named them corresponding to the kind of setup that I have in this code. And I'm going to load those into my workspace ready to run the data itself. So this data here, as I explained, we were looking at 6 measurements at 3 different time points throughout the process of the protocol. So before application, 10 minutes post application, 30 minutes post application. So when I load in these data files, I'm going to order them by region and by time. So it's just going to take a little while to load those, as I'm sure you're aware. MATLAB can take its time. There we go. Those structures are loaded in now. And if I open one of those structures, you'll see it's just like you would expect. You have all your different values. So you have, there you go, you have your coefficient, your absorption coefficient, your frequency, your refractive index, your impulse function, peak to peak, all those things. So that's the kind of data that we want to look at here, and you'll have gained those from your processing. So I've loaded them in here, and now I'm going to form a matrix of those values. So how I've ordered this matrix is I've got each column is a different time throughout the process. So before application, 10 minutes post application, 30 minutes post application. And then they are ordered as going down the L regions and then going down the R regions. You order this exactly how you want to based on the data that you have. So that regions is probably you might want to mess with that matrix structure depending on your protocol, but you want to form a matrix of those values in order to loop through. So there you go. I've loaded them in. I'm going to run that section, and those values are going to be in my workspace now, and I can work with that matrix regions to carry out analysis. We'll move on to that next time one, and I'm going to actually start a new clip here because this one might take a little while. Okay, so then we're moving on to identifying that start point of occlusion. So I spoke earlier about the fact that when you're carrying out analysis on your data, anything that you extract, you want it to be so far past the start of occlusion. All your data, you want to include it from the start of the occlusion process, because that's when the arm or the hand or whatever is on the measurement window. We don't want any of the data before that because that's just air. That's not interesting to us. We want to measure the skin or the sample which we put on the window. So what I want to do is identify the start point of occlusion to be able to carry out that analysis process. And how you're going to do that is by plotting the impulse peak-to-peak function. So I will run this section and then explain what it's done, because I think it's a little bit easier to explain once it's actually run. So you have the time there, and you have the impulse peak-to-peak plotting function. You can find that in that function in the folder. If you want to have a look at it, you feel free. I'm not going to explain how it works here because it just runs it through using the regions above and the time. It's just going to plot those functions. But let's run that section, see the plots that we get, and carry it out. So you can see here, I've got 18 measurements. So I'm going to get 18 impulse plots. So what I'm going to do is I'm going to close a load of them, and I'm just going to look at my first one that I get here. So this is for the region LA, or left top region that we measured for before we've applied any product. And as you can see, this is your pretty standard occlusion curve. So I'm going to talk you through how you can extract the start of occlusion from this curve. So I'm sure Hannah will probably have talked you through this as well at some point. But what you want to do is basically you can see that up here, this is where the arm hasn't been applied to the system yet. And I apply the arm here, and then I get a nice drop, and then you can see here, this is sort of the occlusion process. The peak to peak is going down over time as the skin is becoming more hydrated because it's being occluded. So these measurements lasted around 33 seconds. So that's why we can see that on the time axis there, you can see that's sort of the time frame we're looking at. So if I want to identify the start point of the occlusion process, I'm going to look around here. I'm going to say round about where that big drop ends. I'm going to select around there. So say for this one, I've got an X of 4.333. So this is not super duper accurate because you're using your cursor to find it. You can be slightly more accurate by fitting an exponential curve onto this data and using the start point from that. But bear in mind that you're going to have a bit of an idea of the cutoff first to be able to do that exponential plotting. There is a function that does that in this. I'll come to that later. So using your cursor, you're going to find this is round about the start of occlusion. This is about where that gentle gradient is going to start. So I found that it's 4.333. Now, as you can see, with the time that I've got here, I've got 1 to 200 times 30 over 5. That's basically me converting the 1 to 200, which is just like the numerical scale of there's 200 waveforms, so there's 200, data points, and I'm converting that into time. So 30 over 5, waveform rate over sample averages, so that gives me a scale that's in seconds. So what you want to do to get your value from the X into seconds is you want to times that by 30 over 5 to get that into to take it from seconds back to the kind of MATLAB numerical version that you want to look at. So if I can do this in my command window because it's basically just your own little calculator. So 4.333 times by 30 over 5, 25.998. And that was for my first value that I inputted there, that I loaded before. So what I'm going to do is I'm going to write that in here. I would write 25.998 because that's my start of occlusion there. That's my start point that I've identified. And you're going to repeat that for all of that data that you just loaded. You want to load your start points in the same order as your data files that you loaded so that your matrices correspond in the same way. So you basically want to have region LA. So for this one, I loaded LA before application, then LA 10 minutes after, then 30 minutes after, then LBs, then LCs. I want my values here to be corresponding to LAs, LBs, LCs, because I formed the matrix in the exact same way. You could load them separately and then structure your matrix so that it corresponds appropriately. That might be a little bit complicated though, so just be mindful that those things need to match up. And you can carry that out on all of those graphs that it's going to load for you, and that will run as expected. Note that that impulse peak-to-peak plotting function, what that's doing is, so it's running that regions that you created here, and that's going to run through all the rows, column at a time. So those graphs that I just loaded, that will have given me, number 1 will have been LA before measurement. The before measurement. Then number 2 will have been LB before measurement, then all the way through to RC before. Those are my 1 to 6. Then 7 to 12 will have been LA to RC 10 minutes after. And so I just need to be mindful of the fact that when I input my start points to form that matrix, I'm doing so in a way that corresponds to the data that I'm looking at. So we've already run that section. I have in fact already extracted the start points for all of those all those data points. So all I'm going to do is run that section, load that into my workspace, and then I'm ready to go. So now I've loaded all of my data and all of my start points into the workspace. I've loaded all that data. Now I can do fun stuff. So this next section is going to run a function called analysis data extract, or anal data extract. And that's going to take all of those values that you've just given it, and that's going to kick back the Emacs. So if you have an impulse function, so from the sort of when you put your arm on, you have like a bloop bloop, and you can extract from that the peak to peak, and that's what your occlusion curve is showing. You'll notice that there is a max value, so the top of that peak, and a minimum value. So then those two together will form your peak to peak, your amplitude of the impulse function, and that's your process waveform that the Fourier transforms carried out on using your baseline, your reference. That's the waveform that you're interested in. That's where you're going to get all that data from. So the Emax is that top point, the Emin is that bottom point. That code is going to extract all of those values for you based on where you've set it. So it's going to extract them for however far into occlusion you set. And every so often throughout occlusion, it's going to extract those values. It's also going to extract your peak to peak value. So basically your Emax versus Emin. You should note that because the occlusion curves are a little bit wobbly, because of the nature of the fact that people don't stay perfectly still, it's not going to be a beautiful straight curve. Your peak to peak values might be a little bit funky on a couple of them when they extract, because there could be deviation in that graph and it's going to extract that. Just be mindful of that. That's the peak to peak values that it extracts are still going to give you a pretty decent idea of the data throughout the occlusion process, but be mindful that maybe it would be worth doing Emax minus Emin to sort of match and compare with those peak to peak values, because they should essentially be equivalent. What it's also going to extract for you is the absorption coefficient and the refractive index, and that's going to be, again, from whatever point into occlusion you choose, however frequently throughout occlusion you choose, at the extraction frequency that you have selected. And then what it's going to do is write that data to matrices. So this, I'm looking at what the person we refer to as subject 17, and I've named the matrices appropriately. So this is for a tutorial, so I've just thrown a little tutorial on the end there. So let me run that section. And once that code has run, it might take a little while because you're extracting a lot of data here. If it runs successfully, there you go. You get a little comment in your command window saying data extracted successfully. So once that pops up, you can go, yes, I have my data. I can carry out my analysis now. If you get an error, chances are it's how you're looping through occlusion. So there's a little catch in the beginning of that code that changes how many times you can loop through the occlusion process with the increment that you have. Mess around with the values there, it'll probably fix itself. But again, you have any major issues that you can't find a solution to, feel free to email us. We can always work that through. So let's have a look. Well, I'll start a new clip first, and then we'll have a look through the data that we just extracted to see the form that it's extracted in. So we've just extracted that data by running the section. The values are going to appear in our workspace down here to look at and thing, but we can also look at the text file that it just wrote to. So this is for absorption coefficient, so alpha values. Now, the way that this is structured, the way it extracts that data. So remember I said that we measured 6 regions at 3 different time points throughout the process. So we had before, 10 minutes after, and 30 minutes after applications of a product. That's how this code is structured. This matrix is structured that you've extracted. So those first 6, it's going to go LA, LB, LC, RA, RB, RC. That first 6 rows is for before application. Then I've put in zeros here to separate out that data just to make it a little bit more readable for the user. Obviously, it's a bit of a faff when it comes to code this way, but I think it makes it a lot more readable. There's a lot of human processing with this data. So I'm going to leave those zeros in there. Lines 8 to 13, that's 10 minutes after application, and lines 15 to 20, that's 30 minutes after application. You'll be able to, the structure of this code may change a little bit based on your protocol. So if you have more, if you've done, say, you did 10, 30, 50, 2 hours, 4 hours, then you might need to add in some extra zeros to separate there, and you might need to mess with the structure of that matrix to be able to extract that data. But that's a bare bones, just changing like the odd line here and there. That should be easy to edit for you. And you'll notice that all of the columns here, that is the different time points throughout occlusion. So my first column there, that's at my 5 seconds past the start of occlusion. That's where I started. I said my occlusion delay is 5 seconds into the occlusion process. That's the first data I extract. And then I wanted to do that every 5 seconds past the start of occlusion. So I've got 5 seconds past the start, 10 seconds, 15, 20, 25 seconds. Now, depending on your participant and depending on the start time of the data that you've looked at. So say you've got someone who they didn't put their arm on very quickly and they started really late into the process, that's going to change how many times you can loop through those values. So the dimensions of these matrices may be different depending on your participant. When you carry out comparisons on that data, you're going to have to be mindful of that to think about how you're going to concatenate or compare those matrices, because you can't loop through data that isn't there. So just keep that in mind when you're looking. It's going to vary participant to participant. And I'll quickly just open up, say, our Emaxes. Same with our Emins. Obviously, they're all negative because they're negative values. And let's quickly look. Let's see, peak to peak. Now you'll notice here, there we go, we've got a few down here. There are some really rogue values in here sometimes, and that's what I was talking about with the fact that you have variation in that participant data. Because humans aren't perfect, we can't stay perfectly still. And so that variation may mess up with some things of your data depending on what you're going to use this for. So just be mindful of that, and be mindful of the fact that you may need to put in a catch for this. But if you have your Emax and Emin values, you know the peak to peak. So just think about that when you're extracting your data. I'd say the Emax and Emin are slightly more reliable, so chances are you might just want to calculate the peak to peak from there. And I will have a look. I will join you again in another section to look through what we can do with this data itself now that we have it. Okay, so now we have that data, we can actually do some analysis with it. So what we have set up for you here is a number of functions and .m files which allow you to carry out different tests and different plots using the data that you've extracted or the data that you've just loaded in there. So I will talk you through the plotting functions first, and then we will discuss each of the .m files in turn. I'm not going to go into those with a lot of detail because they are written specifically to this protocol, so you are going to have to edit those to be to fit your own protocol. But I would like to think that they're like somewhat easy to adapt to whatever kind of setup of measurements that you've done. But we'll get to that in a second. Let's look at the plotting. So things that you might want to consider when you're looking at that data, you might want to plot the impulse function, the absorption coefficient, the refractive index. You might want to do an exponential fit on your occlusion curve, your peak to peak that we looked at before, that we had up there. All of these functions here are set up to do that for you based on the data that you've loaded using these values up here. I will in fact change these on the fly because you want these to all be the same, because that's what we have is regions up there. Now, of course, you can change variable names depending on what code that you want to call things. If you input them, perhaps these aren't regions for you. Perhaps these are products or participants or something like that. Depends what you want to compare. So you can load in your data depending on what kind of comparisons you actually want to be doing. So here I've got it loaded for comparing regions. So with each of these functions, they're prepared to load in that data that we've created above and make the plots with that in mind. So I will actually open each of these for you and we can just look at the code itself, because I think that's probably easier than trying to explain them without. So our first one, look at that, it's impulse function plot. So this, you can see it takes the dimensions of the matrix that you've inputted with your data and uses those to loop over both columns and rows. So just like I said for that the impulse peak-to-peak plot code that was in one of the previous clips, what that was doing was looping over every row, going one column at a time. This is doing exactly the same, as are every plotting function that has v2 at the end. So that's version 2. It's set up to work like this. So what it's going to do is it's going to find the time at which you want to plot based on the start points and the time into occlusion that you want to look at. So this is only going to plot 5 seconds into occlusion. This is only looping. This is looping over regions in the data. It's not looping over time throughout occlusion. You can, of course, set it up to do that. You could just loop this function for occlusion delay, and you could like increment every time. I'm sure you'll be able to figure out how you can do that. Just throw it into another for loop in the code, and then as you can see, that's plotting the impulse function for each of them, and what it's doing is it's offsetting each of those impulse functions by 1 on the time axis every time, just to make it easy to see, because they're all going to go on one figure, so you want that to be really easy to distinguish. So let's look at the next one, which is absorption coefficient. So there you go. It's exactly the same structure. It's just using the start and end frequency to plot between that frequency range of interest, rather than plotting against time, because these are frequency domain variables. You can do the exact same with the refractive index. As you can see, there's basically no change in that code. And our last one was the exponential occlusion fitting. So let's open that one. So what this is going to do, this one's slightly interesting in the sense that it's going to plot those peak-to-peak functions for you, but it's also going to plot an exponential fit of that occlusion all over that data. So every graph that you plot, it's going to give you both the peak-to-peak, the occlusion curve, and then a fitting of that. My apologies for getting cut off there, the cheek of this software. As you can see with the fitting of the peak-to-peak function that you're going to look at, that from that fit you can extract a load of different parameters. So you can look at either the fitting parameters, and you could compare them in like a box plot or something like that, and you can compare that across participants, see like how the fit parameters vary across, male versus female or something like that, or just across participants or regions. Or in fact, you could just look at, extracting, say, the peak-to-peak value, the Y value of that peak-to-peak. You can look at extracting that from the exponential fit itself. That might eliminate that problem with the variation that I mentioned previously with the data. So with all those different plotting functions, you can do a lot of different comparisons. And I will, in fact, I think my next thing I will talk you through here will in fact be one of the example codes that we've got, and that is impulse comparison plots. So again, I've set this up to be for one of our participants, the protocol that I'm looking at here, which is comparing skin tones. So this is loaded, in fact, all of our male data. And that's what this is going to do, is it's plotting the impulse function for each of these on the same plot. So it's making use of the sort of, the theory behind that same impulse function plotting function code, and it's allowing me to carry out comparisons of those values across participants. And I'm doing this, in fact, for the same participant for 3 different points throughout occlusion to compare, for 3 different participants, to compare how the impulse function varies both for application of product and time of that product being on the skin, so the hydration, but also how that changes for different participants. So for this one, we were looking at participants of different skin tones. So what I've done here is I've loaded in 3 participants of really different skin tones. So Adam has really like pale white skin. Matthew has a darker complexion. He's Indian, and Pierre is black. So between the 3 of those skin tones that we can look at, we can make comparisons there. And that's just an example of how you can use this kind of code to compare with those plots, to carry out comparisons on your data and draw conclusions from that. Moving away from those plotting functions and examples of that code, you could in fact carry out plotting with something called box plot. So I say moving away from plotting, let's go to another plotting code, shall we? This is slightly different, however, because it's using the matrices of data that you've extracted. So this is carrying out analysis on this data right here, this data that you've loaded. So Emax, Emin, peak to peak Y value, absorption coefficient, N, whatever you're looking at. So that's looking at this instead. I'm just going to close these down, clear out our MATLAB a little bit. So for box plot, this is again set up for our personal protocol. These mostly are just examples for this code that you can adapt to your own protocol, but I hope that it gives you like an idea of what you want to look at. So this essentially is set up to load in that data, to group the input matrices by skin tone, and then to box plot those matrices that we've formed from that data. Box plot is really simple. It's built into MATLAB, so I'm going to leave it at that probably and let you play around with that yourself. You'll also find in this code that in this folder that there are 2 codes called male box plots and female box plots. Again, with the same theory, are reading in those matrices, forming new matrices using that data, grouping them to carry out comparisons, again using box plot, which gives you another set of examples of how you can carry out comparisons using that data that we've got from the analysis data extract function. Some other things that you can do with this data, and probably this kind of, I guess, separate to the plotting that we've done here, is that you can carry out analysis for statistical tests. So one of the biggest things you're going to do is look at the normalized relative change. So for the data that we've extracted, again, those text peak-to-peak files, we're going to read in the matrix for the data that we want to look at. And then what we're going to do is run this. You can run this section here. Again, you need to adapt this to your own protocol. And that's going to calculate the normalized relative change, which tells you basically how hydrated the skin is, the change in the hydration of the skin as a result of the product that you've applied or over time or whatever. So, and then it again forms a matrix of those values, saves it to a text file, and it's also set up to carry out plots for the NRC. What you can then do with those NRC values is statistical testing. So I'm going to take you over to statisticaltests.m, which again is set up for this protocol. So, and I'll be quite honest with you, is not the most glorious code I've ever written. It's kind of messy and it's very long because you have to do a lot of data washing to get to this actual statistical testing. But what I'm going to do is very briefly talk you through how it works so you can see the capabilities of this data, more so because this code isn't really gospel because it only really applies to our protocol at this point, but at least it gives you an example and an idea of how you can use this analysis code to carry out testing on your data and how you can adapt that to your own personal protocol. So here I'm looking at peak to peak. So I'm going to load in the NRC values that I got from my NRC code to read them in as matrices. I'm going to skip over any of the other ways that I could load them in. It's set up to carry out for any of those NRCs. And then I'm going to create arrays to carry out that testing on. Then we're going to group those arrays to make them into categories which I want to compare. So say I want to compare males of different skin tones. I want to create arrays, just like I did for the box plots, of values that I can compare. Same with if I want to do males versus females of a particular skin tone for a particular region at a particular time in the protocol. I'm going to form the matrices that I need from those for both males and females. I'm going to carry on doing that. Trust me, it takes a long time. I believe we cut off just looking through the data washing and just putting things into regions. This is relatively time consuming to write out, but hopefully with what I have, if you can read it, there are a few comments in there, but it's not the most well commented code. If you can adapt this to your own protocol, you can group your data as you wish, ready for comparisons, and then we get down to here. So disclaimer, this is using 3 different types of tests. You're doing Shapiro-Wilk, one-way ANOVA, and Tukey-Kramer. These are all statistical tests that you can carry out. Your Shapiro-Wilk test is telling you whether you can assume that this data is normally distributed, because that assumption is used by ANOVA 1 or one-way ANOVA and Tukey-Kramer tests that you're going to use next. The Shapiro-Wilk code is something you're going to need to download from online, and it downloads with its relevant license. Super easy to do. Just put in Shapiro-Wilk test MATLAB and the code will come up for you to download. It's free. It's it's open access, and that will give you this function here, which has been written by someone far smarter than I. And so you're going to need to download that yourself. I can't put it in this user code folder because it's not distributed like that. You're going to have to download it with your own license, but it's really easy to do. So just be mindful of the fact that you need to do that to carry out this kind of testing. So once you've done that, you can run Shapiro-Wilk on your data, on your groupings that you want to carry out the comparisons on. And then what that will do, as you can see here, it gets you H, P value, and W values for each of the data sets that you run the statistical testing on. Your H value is a logical 1 or 0. If it's a 1, you're good to go. That data can be treated as normally distributed, and you can carry out with your ANOVA and everything tests as you expect to. If it's a 0, your data does not work. You cannot treat your data as normally distributed. Maybe you didn't have enough participants, or say that's why this black male data is commented out. We only have 1 black male in this round of the study, so we can't carry out statistical testing because there's 1 person's data. So you can't, you can't treat one data point as normally distributed. So be mindful of that, and you can see when you run that section, those date values are going to load into your workspace. Check through them, and then you know whether you've got the yes or no to carry on and move over to. I'll skip over this because that's just the same code for different tests. Then we can move to the actual statistical testing on that data that's going to give you plots. So you've got one-way ANOVA and Mulk Compare here. So Mulk Compare is that Tukey-Kramer test that I'd spoken about. And what these are going to do is they're going to basically make their own kind of box plot and give you like a table of values, and that's all information that you can use to inform your analysis based on the sort of the statistical differences between the data sets. So it's going to tell you whether there's a statistically significant difference between, say, your male versus female data, or your white versus Asian male data or something like that. So depending on your groupings and depending on the protocol that you've carried out, you can adapt this code to fit your protocol. But essentially, the theory behind it should be sort of transferable. We carried out clearly a lot of tests here, so it's kind of lengthy. I mean, there's like over 1,000 lines of code here, so it's not the most, it's not the easiest to read. I'm aware of that. So my apologies for if this makes it a little difficult to adapt to your own protocol, but I'd like to think that the logic behind it should be kind of transferable. And that is essentially a summary of our user code. I hope that gives you a rundown of what you can do with this analysis user code and the capabilities of the comparisons you can do with the data that you have. So with those measurements, hopefully this is the main bit that is interesting. This is this section that I'm hovering over here. Up to this point in that code, this is like the difficult bit that you've just gotten out of the way, because this uses a lot of different functions. You'll find them in the folder because you need them on your path to be able to run all of this. Don't worry too much about how each of those are working because they're all just called by the analysis data extract function. If you are interested, feel free to go through them. There's a few comments in there that should explain how they work. But this has essentially done the work for you of extracting that Emax, Emin, peak to peak, absorption coefficient, refractive index. Feel free to add to it and edit the code to call your own values throughout it. But this is essentially giving you it's given you a way to extract that data for you to then carry out the analysis on it. So be it you carry out comparison plots using these functions here, or you adapt one of the .m codes that we've given you for statistical testing or something along those lines. I hope that this has given you a rundown of how to use this code and how the code can be adapted to fit your own protocol so that you can carry out analysis on your terahertz reflection-based measurements, which you've probably carried out using the Gantry system. Thank you very much for taking the time to watch this and listen. As I say, our email addresses are listed right here. Feel free to contact Pierre or I if you want help with anything here, or there's something that isn't quite clear, or there's a bug that you found and it's not really working. Feel free to contact us and have fun with your analysis. Good luck with your project or research that you're carrying out. I hope it's fun.